Let's now try to use implicit differentiation to actually analyze a curve. So this says find where the slope of the curve x squared y equals xy squared equals 4 is undefined. And again, we're not going to solve this equation for y because it's not easy to do. We're going to use implicit differentiation. So to find where the slope is undefined is another way of saying find where the derivative is undefined. And we're going to answer this question by finding the actual point on the graph where the derivative is undefined. So we're going to copy down the equation again. Now I like to leave like some space here because what I'm going to do is I'm going to take the derivative of both sides with respect to x. And the right side is easiest to do first. The derivative of that 4 is just 0. Now, here's where you got to slow down a little bit. I'm taking the derivative of each of these terms, and each term is a product. So I'm taking the derivative of x squared times y first, which means I'm going to have to use the product rule. So maybe even to write that, I'm going to separate it by saying this is d dx of x squared y minus the derivative of xy squared. Now, the thing to pay attention to is every time you're taking the derivative of a y term, after you do its outside part, you've got to times by dy dx because of the chain rule. Remember, we're viewing y as a function of x. So, the derivative of x squared y, well, using the product rule, the derivative of x, well, we'll leave x squared alone. The derivative of x squared will be leave alone. Now we take the derivative of y. Well, it's like y to the 1. So if you bring the 1 down, it becomes 1 times y to the 0, which is just 1. But then I'll have to times by the derivative of the quote inside, which is dy dx. Now that's half of the product rule. Now I'm going to add that to the derivative of x squared, which is 2x. And then I just leave the y alone. So again, that was all just the product rule here. Right, and that was all just this part. So I'm just going to note that was the product rule. And now let's do it over here for the derivative of xy squared. So I'm going to put a negative out here, and I'm going to put some parentheses, just so we know that we're taking the opposite of this derivative, which is probably going to have 2 terms in it. So let's leave the x alone. The derivative of y squared is 2y to the 1, and now the derivative of the inside is dy dx. Plus, because of the product rule, now I take the derivative of x, which is just 1, and I leave the y squared alone. Alright, so there was the differentiation step. Now, our goal is just to do some algebra by isolating dy dx. We got to get dy dx by itself on one side. So this is now just an algebra problem. So let's handle this by getting everything. Well, first I'm going to distribute this negative here, I think. I'm going to distribute that negative to both terms there. So this becomes x squared times dy dx plus 2xy minus, I'm going to write this as 2xy dy dx minus y squared equals 0. And now just get everything that doesn't have a dy dx on the other side of the equal sign. So I'm going to subtract a 2xy and I'm going to add a y squared to give me, it's rated as positive y squared minus 2xy. And then left on this side is x squared dy dx minus 2xy dy dx. And again, we want to get dy dx by itself, or we're going to factor it out. I'm going to factor out dy dx. And that leaves behind an x squared minus 2xy. It's equal to y squared minus 2xy. And now we just divide both sides by x squared minus 2xy to get that dy dx is equal to y squared minus 2xy divided by x squared minus 2xy. For those of you who take the AP exam, what they'll often do in this type of problem is they'll say, show that the derivative of, or show that dy dx is equal to this guy here if, x squared y minus xy squared is equal to 4. So it's good because they tell you what the answer is and you just have to show the steps. Our question, or our problem, is a step further because we need to actually find where this derivative is undefined. Well, this derivative is undefined anytime the denominator is 0, right? So dy dx is undefined when that denominator, x squared minus 2xy, is equal to 0. So let's find out when that happens. So that's going to happen when, if we factor, that's going to happen when x times x minus 2y is equal to 0. So that's going to happen when x equals 0 by the zero product property, or when x equals 2y. So we can do better than this, though. That is a description of where the derivative is undefined. By the way, notice when you plug 0 in to this equation up here, you get 0 squared y minus 0y squared equals 4. You get 0 equals 4. So I'm going to just say when x equals 0, we get 0 squared times y minus 0y squared equals 4. We get 0 equals 4. What that tells me is that there is no point on this curve that has an x-coordinate of 0, which means that it probably hasn't, well, it definitely doesn't have a derivative there if it doesn't even have a point there. All right, so it's not defined at x equals 0. To find where it's not to find the other places where it's not defined, we're going to have to plug 2y in for x. So I'm going to say when x equals 2y, plugging that in, I'm going to get 2y squared y minus 2y times y squared equals 4. And this becomes 4y cubed minus 2y cubed equals 4, which means that 2y cubed equals 4, which means that y cubed dividing by 2 equals 2, which means that y is equal to the cube root of 2. And since x is 2y, that means it equals 2 times the cube root of 2. So, in conclusion, there we go. In conclusion, we can say that the slope is undefined at x equals 0, since the curve is undefined there. And at the point x equals 2 cube root of 2, comma, y is the cube root of 2. So my guess is that at this second point, there's probably a vertical tangent. So on the next page, I actually have the graph, and you can see that at the point 2 cube root of 2, cube root of 2, we'll have a vertical tangent. Yeah, and so here the 2.52, comma 1.26, those are approximations of the cube root of 2, 2 cube root of 2 and the cube root of 2, and you can see you got your vertical tangent there. And notice there's no point on this graph that has an x-coordinate of 0 because you've got a vertical tangent there. So there's a first example of a problem involving implicit differentiation, and it helped us analyze this curve without actually having to solve it for y. So there's a lot of mechanics there. You might want to slow that down and do a couple practice problems to make sure you really get it. In the last video, we were analyzing the curve x squared y minus xy squared equals 4. and we used implicit differentiation to find its derivative, which is given here. So if you want to see that derivation, go ahead and go back to that prior video and watch it. But what we want to do now is answer this question, which is another common question, find where the curve has horizontal tangents. So let's remind ourselves what that means. A horizontal tangent is going to occur when the derivative is equal to 0. So horizontal tangents occur where dy dx is equal to 0. So if we take y squared minus 2xy divided by x squared minus 2xy and set that equal to 0, well, we could times both sides by x squared minus 2xy, and what we would get is that y squared minus 2xy equals 0. In other words, the only way that can be 0 is if the numerator is 0. Now, by the zero product property, well, first let's factor. That means y times y minus 2x is equal to 0, which means that y equals 0 or y minus 2x equals 0. Now, this is where you got to be a little bit careful because you got to make sure, this process doesn't take into account the fact that some of the values you find might be places where the curve doesn't even exist, right? So, for instance, if I take y equals 0 and I plug it in, when y equals 0, you get x squared times 0, so I'm plugging this back into the original equation, minus x times 0 squared equals 4. The left side is just 0, and you get 4. So that means that y equals 0 does not correspond to a point on the curve. So that just means that there's no point on this curve that has a y coordinate of 0. And we'll see that when we look at the picture later. When y equals 2x, however, or when y minus 2x equals 0, again, that means that y equals 2x. When y equals 2x, that means we're going to go ahead and put 2x in for y in this equation. So that means that x squared times 2x minus x times 2x squared is equal to 4, which means that 2x cubed minus, why did it look like I did something wrong? Oh, I didn't. Minus 4x squared times x, so that's 4x cubed equals 4. So that means that negative 2x cubed is equal to 4, which means that, sorry about that, which means that x cubed, if we divide by 2, is equal to negative 2. And that means that x is equal to the cube root of negative 2. And since y is just 2x, that means that y equals 2x, which would be 2 times the cube root of negative 2. So we've got horizontal tangents or a horizontal tangent at the point x equals cube root of negative 2 and y equals 2 cube roots of negative 2. So that should be at some point in the third quadrant, and on the next page you'll see that we can see that point, and we can see that the curve has a horizontal tangent there. So here you can see at the point, this is supposed to be the point negative cube root of 2, negative cube root of negative 2, negative 2 cube root of negative 2. You can see there's a horizontal tangent there. And you can see that when y equals 0, that's just the x-axis. There's no horizontal tangent there. There's an asymptote there. There's no curve there. So we had to check that so we could rule it out. There's only one point of tangency for which the tangent is horizontal, and we found it here.